Okay, in today's video, I kind of want to go back to something that we did previously in part C with thermal resistances. And I want to start off by talking about resistances in series and then in parallel. So let's go back to our example from part C where we were talking about series. I'm going to draw out our same example of our glass mug that we had. So we know that we had coffee, our glass mug, followed by an insulating sleeve, and finally air. And we know that we had heat loss via convection through the coffee, heat loss via conduction through the glass, heat loss via conduction through the insulation, and heat loss via convection to the air. And this time, when I am going to be talking about our temperatures, I'm going to label the temperature of coffee as T1, the temperature at this surface as T2, the temperature at this interface between the solids as T3, the temperature at this surface as T4, and the temperature of the air as T5. And we said that at steady state that all of these convection and conduction terms were equal to each other. So we had a single heat flow term Q equal to the heat loss via convection through the coffee, which is equal to heat loss via conduction through the glass, which is equal to heat loss via conduction through the insulation, which is equal to heat loss via convection to the air. And as we said before, this is analogous to electrical circuits. So we had Ohm's law, which is the change in voltage is equal to our current multiplied by our resistance. And we said that this is analogous to here, our temperature, our change in temperature is our driving force, equal to our heat flow Q multiplied by thermal resistances. And we know that for resistance, we had different equations for both conduction and convection. So for conduction, we know that we can find that heat flow using Fourier's law. So that was our heat flow is equal to our thermal conductivity multiplied by the area, multiplied by our temperature gradient, which we said that if we have this thickness of the glass and a thickness of this insulation, if we knew the temperature here, we knew the temperature here, we knew the temperature here, and we subtracted those and divided by our thickness, that became our change in temperature with respect to position. And same for insulation. So we said that this was the change in temperature delta T over some thickness L. And for convection, we had our heat flow is equal to a heat transfer coefficient multiplied by the area multiplied by a change in temperature. So if we kind of manipulate this equation to look more like this, we're going to have that our delta T, our driving force, is equal to our heat flow multiplied by the thickness divided by our thermal conductivity multiplied by area. Same thing down here, we had our driving force, our change in temperature, is equal to our heat flow multiplied by 1 over the heat transfer coefficient multiplied by the area. So again, as we can see here, we have a driving force, our current, which in this case is Q, and a resistance, which for conduction is the thickness over the thermal conductivity multiplied by the area, and for convection it is 1 over the heat transfer coefficient multiplied by the area. So let's write out our resistance terms for each of these. So first we had convection. Through the coffee. And again, that is a convection term, so we're going to have to use this for our thermal resistance. So it's going to be 1 over the heat transfer coefficient for coffee multiplied by the area. And our conduction term, our heat loss via conduction through the glass, is going to be written as the thickness of the glass divided by the thermal conductivity of the glass multiplied by the area. Our resistance term for the heat loss via conduction through the insulation can be written as the thickness of the insulation divided by the thermal conductivity of the insulation multiplied by the area. And finally, our resistance from the heat loss via convection to the air can be written as 1 over the heat transfer coefficient of air multiplied by the area. Now, if we want to get this equation to be in terms of Q, as we have Q on the left side over here, that's going to be Q is equal to the change in temperature over the resistance. So let's write that out for each of our scenarios. We're going to have the Q convection through the coffee is equal to our temperature difference, which in this case is going to be T1 minus T2. All over the thermal resistance of the coffee. Now we're going to have our heat flow via conduction through the glass, which again is equal to our temperature difference, which is now T2 minus T3. All over the thermal resistance of the glass. Then we're going to have our Q conduction through the insulation, which is equal to this temperature difference, T3 minus T4. Over the thermal resistance of the insulation. And finally, we have our heat loss via convection to the air, which is equal to our final temperature difference, T4 minus T5. Over the thermal resistance of the air. So if we want to start talking about total resistance in a series, we know that our total in series is simply just the addition of each individual resistance. So to model this, I am going to multiply each of these resistance terms over to their Q term and add them. And we know that just like in a series circuit, if we're relating our Q, our heat flow term, to current, in series current is not changing, it is always constant. Therefore, we can have a singular heat flow Q multiplied by the sum of our resistances. So the resistance, the thermal resistance due to convection through the coffee, plus the thermal resistance from heat loss via conduction through the glass, plus the thermal resistance from the heat loss via conduction through the insulation, plus the thermal resistance from heat loss via convection to the air. This is going to be equal to the sum of our temperature differences. So if we add all of these temperature differences together, we can see that T2 cancels, T3 cancels, T4 cancels, and we're simply left with T1 minus T5. So our overall temperature difference. So as we can see, this is related to our total resistance. So our total is simply the sum of each of our resistances. So our thermal resistance from the heat loss via convection through the coffee, plus thermal resistance of our heat loss via conduction through the glass, plus the thermal resistance of the heat loss via conduction through the insulation, plus the thermal resistance of the heat loss via convection to the air. And we already wrote out these terms up here, so we can simply just take those and plug them into our equation for total resistance. So total resistance is going to be equal to 1 over the heat transfer coefficient of coffee multiplied by the area, plus the thickness of the glass divided by the thermal conductivity of the glass multiplied by the area, plus the thickness of the insulation divided by the thermal conductivity of the insulation multiplied by the area, plus 1 over the heat transfer coefficient for air multiplied by the area. And as we can see, we have this constant area term that can be taken out of our equation. So we're going to have our total is equal to 1 over our area multiplied by 1 over the heat transfer coefficient for coffee, plus the thickness of the glass divided by the thermal conductivity of the glass, plus the thickness of the insulation divided by the thermal conductivity of the insulation, plus 1 over the heat transfer coefficient for air. And that is how you find thermal resistance for something that is in series. So now I want to talk about what happens when we have heat flowing in parallel. So I'm going to write out an example to help us. So we're going to have two different materials here. We're going to say on top there is wood and below it is glass. They're going to have differing thermal conductivity. So we're going to say for wood it's going to be denoted with K wood, and glass is going to be K glass. They're also going to have different areas, so we're going to put this as A wood, and this area is A glass. And then they're going to have different thicknesses again. So this is going to be the thickness of the wood, L wood, and this is going to be the thickness of the glass, L glass. And we can say that on the left and right side we have two different temperatures, so we'll put T1 and T2. And we can see that we're going to have heat flowing via conduction through the wood, as well as heat flowing via conduction through the glass. So as we said before, this is analogous to electricity with Ohm's law. And we know Ohm's law is the change in voltage, which is equal to the current multiplied by the resistance. And relating this to heat, our equation was the change in temperature, which is our driving force, is equal to our heat flow Q multiplied by a thermal resistance. And thinking back to circuits, if we have a circuit that's in parallel, we can say that our total current is equal to the sum of the currents. Let's say there's two currents, so it'd be I1 plus I2. And if we rearrange this equation to be in terms of current, it's going to look like I is equal to delta V over the resistance. So we can change this to be in terms of that. So it's going to be our change in voltage over the resistance at resistor 1 plus the change in voltage over the resistance at resistor 2. And once again, this is equal to our total current, so we can say this is equal to our change in voltage over the total resistance. Our change in voltage terms are all the same, so we can take those out, and we are left with 1 over our total resistance being equal to 1 over the resistance at resistor 1 plus 1 over the resistance at resistor 2. Now if we take this equation and put it in terms of our current, or in this case Q, our Q total heat flow is going to be equal to the change in temperature over resistance 1 plus the change in temperature over thermal resistance 2. And our resistance 1, we're going to say, is the resistance of the wood. And our resistance 2 is going to be equal to the resistance of the glass. And if we write those out, we said those are both heat is traveling through conduction there. So we're going to have our wood is going to be equal to the thickness of the wood divided by the thermal conductivity of the wood multiplied by the area of the wood. Likewise, the thermal resistance of our glass is equal to the thickness of the glass divided by the thermal conductivity of the glass multiplied by the area of the glass. If we plug these back into our equation and change Q total to be in terms of the temperature change over the total thermal resistance, we can find that the temperature change over the total thermal resistance is equal to the temperature change, or driving force, over the resistance of the wood, which we said is the thickness of the wood, divided by the thermal conductivity of the wood, multiplied by the area of the wood, plus the change in temperature or driving force over the thickness of the glass over the thermal conductivity of the glass multiplied by the area of the glass. Just like we did over here with our change in voltage, we can cancel these change in temperatures. Then we're left with 1 over R total is going to be 1 over the thickness of the wood divided by the thermal conductivity of the wood multiplied by the area of the wood plus 1 over the thickness of the glass divided by the thermal conductivity of the glass multiplied by the area of the glass. And that is how you find the total resistance for something that is in parallel. Okay, now for this example, I want to talk about when we have both series and parallel together in the same example. So let's imagine we have this house that has double pane windows followed by a wall. So for the double pane windows, we're going to have our first glass pane, which we'll denote as glass 1. And then between the second pane, there's going to be argon. And then our glass 2. And then up here, this is going to describe our wall. And our wall is going to have material, let's say this is brick, followed by insulation, and then studs. And then we're going to have 2 different temperatures on either side. And we're going to denote the temperature on the right as temperature on the outside, so outside air. And this temperature is going to be from the inside air. Now we can start thinking about our resistance right here for our window. So the thermal resistance of our window is going to be found by adding up all of the convective and conductive heat terms, because this window is in series, so we can just simply add them up. So we're going to have the thermal resistance via convection from the inside air to glass 2. And then we're going to have thermal resistance via conduction of glass 2. Thermal resistance via convection from glass 2 to the argon. Thermal resistance via convection from the argon to glass 1. Thermal resistance via conduction of glass 1. And then finally, thermal resistance via convection from glass 1 to the outside air. And like I said, these are all in series. So our total for the window is just going to be the addition of all of these thermal resistances. And next we're going to be talking about the thermal resistance of this wall. So we're going to write thermal resistance of the wall. And this is going to be equal to the thermal resistance via convection of the inside air to the studs, the thermal resistance via conduction of the studs, the thermal resistance via conduction of the insulation, the thermal resistance via conduction of the brick, and finally the thermal resistance via convection from the brick to the outside air. And once again, all of these for our wall are in series. So these resistances can just be added to find the total resistance of the wall. And if we want to find the total resistance of our entire process right here, we can see that the wall and the window are parallel to each other. So in order to find the total resistance for that, we're going to have to use our equation for total resistance for something that is in parallel. So we're going to have 1 over R total is going to be equal to 1 over the resistance of the window plus 1 over the resistance of the wall. And that is how you find the total thermal resistance of an example that includes both series and parallel terms.